In this video, we're going to implement a simple neural network that is trained to mimic a sine function with the backpropagation from scratch in Python using only NumPy. We will go over the theory and then create our own dataset of some scattered points, which the network then learns after about 30,000 epochs to mimic, as you can see here in this function. A particular emphasis of this video will be on the backward pass and how we obtain gradient estimates that feed our gradient-based optimizer. Let's get started. Hi and welcome to this new video. Neural networks are a type of machine learning model that allows us to fit data in regression problems, but also are applied to classification problems. A key aspect of applying neural networks is the training of those networks, which is a non-convex, so a complicated optimization problem for which we typically use gradient-based optimization algorithms. And the method of obtaining these gradients is a really elegant approach, typically called backpropagation. It's a special case of automatic differentiation, which allows us to differentiate computer programs and take derivatives. But I also think it is too often abstracted away. It can provide so much more detail by looking into it in great detail, which is what we want to do in this video by coding it from scratch in Python. And for this, we will restrict ourselves just for a super simple scenario. We will look at the architecture, which is called a multi-layer perceptron. It's a standard feed-forward neural network, nothing special here. And we also won't do anything data science related, no train validation test split, no regularization, no stochastic mini-badging. And as our optimizer, we will just use a simple gradient descent with a constant learning rate. And there are no further training modifications. But even in this super simplified scenario, we will see that the network is able to mimic the dataset we are given it. And this dataset will consist of X and Y samples, so our network should have a property to map from a scalar to a scalar, so it takes a coordinate X and should produce an output value Y, and in the best case, the functional relation that the network learns should mimic the sine function, which we also use as a ground truth to draw some data from it, which we will corrupt with some noise. Then our multi-layer perceptron is given in terms of weight matrices and biases. We will see them in a second, and we will use the sigmoid activation function. A nonlinear activation function is crucial for neural networks in order to give them their learning abilities. And the sigmoid activation function has a really nice property in that its derivative can be expressed by the original output multiplied by 1 minus its output. And also take care that even though our network is a scalar to scalar mapping, we will still feed it with matrices. And this is in order to represent common conventions that you have, so that we will use matrices X being n by 1 dimensional, so it is a column vector, and all the rows contain the badges. So in essence, these are independent samples that we've shown that in their totality match somehow the shape of a sine curve. And for each of those input samples, we have a corresponding Y output sample, so the Y will also be a matrix of n by 1 dimensional. Then the neural network consists of a forward pass. This is basically the evaluation of a network. Or in other words, if someone provides you with perfectly trained parameters, and the parameters of the neural network are the weights and biases, this is what you would do in order to query the network for new inputs. Basically, we will step through some layers. So here I've decided to restrict ourselves to 3 hidden layers, and we arrive at the first hidden layer state by taking our input and multiplying it with a weight matrix. And we are doing a left multiplication here. That's because our input matrix is of the convention batch by spatial, and so we have to multiply with the matrix from the right, which transfers our dimension into the first hidden or latent dimension. Once we are in our first hidden dimension, we will then add a bias, and this bias is given in terms of a vector which has the same size as this hidden dimension. So in essence, this is a batched addition, so we will add the vector to each of the batch entries, and here in Python this will automatically be broadcasted. NumPy will interpret this as adding the vector to each of the rows, because in the rows we always have our batches. Then as the last step in this transformation, we will apply our nonlinear activation function. So this is the sigmoid function, and then we will get the activated state in the first layer. And this process is basically repeated. We then take this activated state, left multiplied with the matrix, get an output, then we will add our bias in each row, again the same activation function, and we do it another time. And then we have our last layer, which is the output layer. It consists of the same multiplication with a weight matrix and a bias as well. But then we will not use the sigmoid activation function, but we will rather use the identity function in order to not clip our values to -1 and +1, but allow them to take any value. This is the forward evaluation of our network. If we now want to compute a loss, so in other words, a metric which shows us how well we did or how close our network is to the data that we provided with, is that we will then take an element-wise difference of the output of the network with a reference solution which we have at hand. We will then element-wise square it and take the mean over all axes. And by over all axes, I mean we will take the mean over the batch dimension as well as over the spatial dimension. I mean, here in the spatial dimension, we only have one entry, so there is not much to take a mean over, but just in general, and then we also add a factor of 1/2. This is the forward pass, and as said, we would use this approach if we are already provided with trained matrices and biases. So the parameter set of our neural network consists of the weight matrices and biases we have here. And if we are provided with them, we could just use the forward pass to evaluate the network at new samples. However, we are interested in training the networks, so we are interested in weight matrices and biases that minimize our loss. And in order to perform this optimization, we need a starting point. And typically for neural networks, this is done by a random initialization of the weight matrices and biases, which we will do in this second important step for neural networks. And we will use a method that is due to Xavier Glorot. And basically this just uses a uniform initialization of the entries in the weight matrix. So all of the entries of the weight matrices are sampled independently from this uniform distribution between a negative limit and a positive limit. And the limit is given by the size of the matrix. So basically we have the fan in and the fan out. This basically means how big of a layer transition we happen. So if we transform between very large hidden dimensions, then we want our values to be chosen small in order to give the initial output of the network a relatively small magnitude. And this is basically encoded in this weight initialization. We will not initialize the biases, so in other words, we will just keep them 0. Now let's come to the heart of training neural networks. It's the backward pass. As said, the essential idea of training neural networks is finding parameters, so weight matrices and biases, that minimize the loss. And as with a lot of optimization problems, there are various number of optimization algorithms. Here for neural networks, one typically uses gradient-based optimization. So we need this gradient information, which is provided by the backward pass. And I think this is a beautiful concept. And the idea of obtaining gradient estimates in a number of cost, which is only a constant multiple of the network evaluation, is a really general concept that you find in science under different names, and also for backpropagation this has been reinvented multiple times. Still, it is an interesting idea. So basically, how does that work? The backward pass, as with all reverse mode automatic differentiation, needs a forward pass first, but we don't do the forward pass as we would do it naively, but we need to save all activated intermediary states. So you will save the y1 hat, you will save the y2 hat, y3 hat, and y4 hat, because we will need it. With those saved, we can then start the backward pass, and this basically operates in the reverse order. So we will start at the original output of our forward pass, which was a loss, and assign a cotangent value to it. A cotangent value you can think of in that sense as being the loss derived with respect to that quantity. So if we have an L bar, this basically means the derivative of the loss with respect to L. So the derivative of L with respect to L is obviously 1. Then we have the derivative of the loss with respect to the output of the final layer. So this is y4 hat bar. And here we will find the rule that we will get this quantity by multiplying the L bar, the cotangent of the loss, from the left with the original difference divided by n. This is basically the pullback rule or the backpropagation rule that we find for the L2 loss. I will also give some more details in a second, don't worry. So let's look at the primal pass again. So we had the y4 hat, for which we now have a cotangent information. Next step is to get the y4 tilde, and for this we need to backpropagate over the identity function, and this is relatively straightforward. This backpropagation is just as if we would multiply it with 1, so no modification. In that sense, the y4 tilde bar is exactly the y4 hat bar. Now it gets a bit more tricky. Now here we have an operation that is an addition, and it's not just any addition, so it basically takes the y4, which is a matrix which has the badges in the row, and then row-wise adds the bias. So we need to backpropagate both to the y4 in order to go back in our chain, as well as to the b4 in order to get the gradient estimate. Let's first do the y4. For the y4 it's straightforward because it is just an addition, and so the backpropagated value, so the y4 bar, is exactly the y4 tilde bar, whereas however for the b4 bar we need to sum over the badge dimension, because originally our bias vector is a vector and this y4 tilde bar state is a matrix because it contains all the badges, but the bias only applies to the hidden dimension. So it was kind of scattered over all the badges. So in order to get its contribution, we will sum over the badges. And by this we then also found the first gradient estimate. So basically, as said, the b4 bar can be interpreted as the loss derived with respect to b4. So this is a first part of our gradient estimate we will then use in order to update the weights. Let's go to the next step. So basically now we have our y4 bar, and then we have to backpropagate both onto the y3 hat bar as well as the w4 bar. Let's first do the y3 hat bar, and in order to get that, we will left multiply this with the weight matrix transpose. So we will need the weight matrix again, but this time in the transpose state, and it's left multiplied again. Also more details on why this is the case in a second. Then we also need to backpropagate into the matrix, so in order to get our gradient estimate, and this one is done by taking the y4 bar and then doing an outer product with the y3 hat, so the activated state from the previous layer, so previous in chronologically ordered. And we need to do an outer product in order to get our matrix here. This also shows why we need to save the activated layer states, because we need them again here. So basically this is that value which we have in our tape, in our memory, and we need it in order to get back into this matrix, or into the cotangent state of this matrix, and then we found another part of our gradient estimate. Now we are in the previous layer, and now we have to backpropagate over the sigmoid function. And again, recall the sigmoid had this nice property that its derivative is given as the output multiplied with 1 minus the output. And the output of our sigmoid was exactly y3 hat. And we had that saved, so we can reuse it, which means that we get the y3 tilde bar by taking the y3 hat bar and then multiplying it with the derivative of the sigmoid, which is exactly given as y3 hat, element-wise multiplied by 1 minus y3 hat. The next steps are similar to the previous layer. We again get the cotangent on the bias, we get the cotangent on the y3, etc., etc. And the next layer is exactly the same, just with an index swapped. On the way of going backward through our layers, we get our gradient estimates. So here we had the b4 bar, the w4 bar, b3 bar, w3 bar, and so on. And we go all the way back until we get the w1 bar. And if we were interested, we could also get the cotangent value on the input of the network. But this is not relevant for us because we are not optimizing the input, but we are rather optimizing the parameters. But if we wanted to, this could be done that way. So this is the backward parse that we do. Now we have these cotangent estimates on the parameters, and this allows us to do learning, and learning is nothing else than solving an optimization problem. Here in that case, approximately. So how does that work? So we will do our initialization according to the Xavier Glorot initialization. Then we will run the forward and the backward pass. And we will do this here together for all samples. And now we basically have the cotangent for each of the parameters. And then we can update the parameters by taking their original state, subtracting the cotangent state multiplied with a learning rate. And then this is basically a loop which we repeat over and over again until the loss value is sufficiently decreased. Then we hopefully found parameter estimates which constitute to a neural network that somehow mimics the sine function. Hopefully. Let's see. Okay, as promised, some more details on the backward pass. Essentially, we need 6 operations here, which might be a bit tricky and counterintuitive at first. So we need a pullback operation. And so whenever I say pullback, this is basically a rule that one derives in order to move cotangent information from the output of a primal operation to the input of a primal operation. The first one we need is to go from the loss cotangent to the guess cotangent, and we've seen that. Then we need something over a broadcasted function activation and so on and so forth. If you want more details on why these rules are the way they are, I linked some YouTube videos of the channel where I derive these rules in great detail, and I hope they provide some additional insight. You will find the Jupyter notebook together with the links on the GitHub repo of the channel. And also some final remark I want to leave here, because I just think it's so interesting, is that these ideas of obtaining gradient estimates of operations, arbitrary operations, not necessarily neural networks, but also scientific simulation, and you name it, is something that has been reinvented in science multiple times under different names, which is also a little bit unfortunate because we have some conflicting naming schemes. So as you might have noticed, sometimes I say pullback, sometimes I say backprop. You might also hear a joint or a vector Jacobian product. I would encourage you to check out this Wikipedia link and go over that. It's a very deep rabbit hole if you want to dive into that, but this just as a side note. So finally, let's get started with the actual coding. So let's go down and remove this nice hello world here and start by importing our packages. So we will need NumPy and we will import it as NP. And then we will also need matplotlib.pyplot and we will import it as PLT. Let's execute that, and then we will set the random seed of NumPy to 0. This is just for reproducibility, because as said, we will do some random initialization, and so if you run this notebook on your machine, you could get the same results. Then let's set some hyperparameters. So let's say the number of samples we want to use shall be 200. Then we define the architecture of our MLP by the number of layers. So we will first have a 1-dimensional input layer. Then we have a 10-dimensional hidden layer, another 10-dimensional hidden layer, another hidden layer, and then a 1-dimensional output layer. Then let's set the learning rate to 0.1. The learning rate was basically the scalar value with which we multiply the gradient before we use it to update our parameters. And then let's set the number of epochs over which we want to train to 30,000. Okay, let's generate some data. And for this generation, I want to remind you this Python convention uses batch by spatial. This means that if we draw our data set, we will have the batch dimension in the rows of the matrix and the spatial dimension in the columns. So let's draw some X samples by using numpy.random.uniform to draw from a uniform distribution. And here I want to draw values between 0 and 2 times pi. And I want to draw values that fit into a NumPy array, which is of n samples by 1. So because we have our 1-dimensional input. So then let's get some corresponding y samples by taking the sine function and applying it to the x samples. So this produces some ground truth, but now we would have some uniformly scattered values in x with a correct value in y. So we will corrupt it with a bit of noise by doing plus and then choose numpy.random.normal for a normal distribution, which is located at 0, so with a 0 mean value and with a standard deviation of 0.3. And it shall be of the same size. So we will have n samples by 1. Shift Enter executes the cell. Let's take a look at the data by doing plt.scatter on x samples and y samples. And here we go. Basically, this is the data we have provided. So we see that this approximately follows a sine curve on the range from 0 to 2 pi. So let's see how good the network is at learning this. Okay, before we continue, let us define the nonlinear activation functions. So let's just call it the activation functions. And let's define first the sigmoid function by using a lambda. So the sigmoid was defined by taking its input, and then the operation it does is 1 divided by 1 plus NumPy dot exponential of minus x. And then let's also define the identity function, which is just the lambda x and returns x. So this is the function, or the, in quotation mark, activation function we will use for the final layer. Shift Enter executes that. So now the first step is to initialize our parameters. So this is the initialization of weights and biases. And we will pack these parameters into lists. So let's create a list with our weight matrices. So this will be an empty list for now. Then we have the bias vectors, which we should also pack in a list. And we have our activation functions, which we also pack in a list. Okay, then we can iterate over the matrices and biases that we need. For this, we will do an iteration over the layer transition. So if we look at the layers, we basically have 1, 10, 10, 10, 1. And out of those, we have 4 transitions. So we have a transition from 1 to 10, from 10 to 10, from 10 to 10, and from 10 to 1, which means that we need weight matrices and biases and activation function for each transition. And in order to do that, we will cleverly iterate with the zip iterator. The zip iterator takes 2 iterables, and we will use one iterable, which is our layers constant, but excluding the very last. And then we will take the layers constant, but excluding the very first. And then basically what we get by this is an iteration over the fan in and the fan out. And then we can use this fan in and fan out to define the kernel matrix uniform limit. So the kernel matrix uniform limit, and essentially this will be the limit of the uniform distribution from minus the limit to plus the limit, from which we will independently draw the entries of the weight matrix. And this is given as NumPy dot square root of 6 divided by fan in plus fan out. Then we will perform our Glorot or Xavier Glorot uniform initialization. So we will get the weight matrix W by doing NumPy dot random dot uniform, and the low will be minus the kernel matrix uniform limit, and the high will be plus the kernel matrix uniform limit, and the size that we want to draw will be fan in by fan out. This gives us the weight matrix for the current layer transition. So for instance, for the first layer transition between 1 and 10, we will get a 1 by 10 dimensional matrix, with the limits being from minus square root of 6 divided plus 1 plus 10 is 11, so square root of 6 over 11. This is already not a nice number anymore, but at least I hope this gives you a perspective, and the size of the matrix is clear. And then when we go on to the next layer transition, our matrix will be 10 by 10 dimensional, then it will be 10 by 10 dimensional, and then finally it will be 10 by 1 dimensional. Okay, this is the weight matrix. Then we will have our zero bias initialization. So we say B is NumPy dot zeros, and now we need to select it as fan out because the bias is applied once we have transitioned into the dimension of this hidden layer. So it has the dimension of the hidden layer, which is fan out. And then we can take our lists and append the weight matrices and biases. So weight matrices dot append W, bias vectors dot append B, and then I will also, for simplicity, append the sigmoid function. So activation functions.append sigmoid, but we need to make some modification because now we have sigmoid in each layer, but for the very last layer, which is basically given at -1 of the list, we will just use the identity. Okay, shift enter, let's see, that works. Okay, with the initial state of our weight matrices and biases, we can define a function which evaluates the network forwardly. So let's call it network forward, and it shall take an x value, it shall take weights, biases, and activations. And then let's use a temporary variable which defines the current state that we are through the network. So if we go to our forward path, we see that we basically have these subsequent operations. So this variable a shall represent each of these individual states. But since we don't have to save anything in the forward path, let's just call it a. And the initial state of a will be x. And then basically we will iterate over weight matrices, biases, and activation functions in, again, a zip container of weights, biases, and activations. And then basically we first do our multiplication with the matrix. So we will say a matrix multiplied with w. Then we will add our bias by saying a is a plus bias. And here NumPy already broadcasts this addition over the rows as mentioned earlier. And then finally we will get the activated state by calling the current activation function on a. So this basically loops over the layers in our network, and then we will return a. This is our network forward function. So let's see how the network performs on the samples that we have. So again, for reference, let's scatter our x samples and y samples, and then we can scatter the x samples together with what the network thinks where the corresponding y position would be by calling network forward on x samples, weight matrices, bias vectors, and activation functions. Let's hope that works. Okay, here we go. So the blue points again are our data, which we want to use to train a network, and the orange ones are the output of the network. So they lie mostly in a straight line, so there's nothing too fancy here, but this is also good because this initial state of the parameters is quite nice, because the network could also say, oh yeah, my values are at -100, or could have some crazy oscillation. So this is a decent start for our optimization, such that the network can learn a sine function. Let's use this occasion in order to define our loss function. So let's call this the loss forward. So this is the forward evaluation of our loss, which takes a y guess, so the output of the network, as well as some reference data. And then we compute first the delta, so the difference, which is y minus y reference. And then we will return 0.5 times the mean of this delta being element-wise squared. And by calling the mean function on the delta, and of course here we need y guess, I see, and by calling the mean function on the delta, it will already apply the mean to all axes, because the delta will be a matrix which has batch by spatial again, and I mean the output is just one spatial dimension, so this is a rather trivial mean over this column axis, but NumPy already conveniently does that for us. So let's try out the function by calling loss forward on first the network prediction. So we will do network forward on the x samples together with the weight matrices, the bias vectors, and the activation functions together with the y samples. And let's see, so our initial loss is 0.815. So there's not much meaning to it. It is good to have a loss, an initial loss at the order of 1, because such then we will never run into many floating point error problems. But for now, this just has no meaning for us. The only point is that we will hope that this loss goes down by orders of magnitude. So we want to have it, let's see, 10 to the -4. Let's see how good we get to there. Okay, before we now start the backward pass, I first want to define the backward function of the loss by saying loss backward. And this loss backward also takes a y guess and a y reference. And then let us look at the backward pass. This is a little bit intermixed here. So basically now we want to get the cotangent on the guess. So this loss backward should take the prediction as well as the correct value. And then, we will assume that the L bar is 1 because we always want to have the gradient. So it will compute that, which is just the delta divided by n. And n was the total number of entries over which we did the mean operation. And since we only had one spatial dimension, n essentially refers to the number of samples. Okay, let's go down. Let's first define the delta, which is y guess minus y reference. Then we can get n by just saying this is delta dot size. We know it will be the number of samples, but this just keeps it more general. And then we can return delta divided by n. So this then gives us the cotangent guess. So right now executing this function wouldn't make much sense because it's just a bunch of numbers. But we will use it in our forward and backward pass, which is the next function. So this is define network forward and backward. And by using this name, I also want to highlight that doing a backward pass always requires us to first did a forward pass and saved some intermediary values. And as mentioned earlier, this is the general theme of reverse mode automatic differentiation, that you need to somehow go through the primal pass, so the forward pass as well, and save values. In our case, for networks and for the way backpropagation was originally introduced, it is just saving the activated states. Nevertheless, let's define that, and this takes an x as well as a y reference. Then we need the weights, the biases, the activations, and the activations derivatives. I will come to that in a second. And then first, we will do our forward pass again by first defining a to be x again. So this is again the temporary variable we will use to go through the forward pass. But then importantly, we will store the intermediate activated states for the backward pass. And for this, we will use a list and say layer states. And we will start with a here, because a is x and we also need x, so the input to the network, in order to get the very first weight matrix. So if you look here, you see that the cotangent weight matrix is the cotangent y1 state in an outer product with the input x. So we will also need that one here. Okay, then the operation is quite similar. So we will do for wbf in zip weights, that needs a comma, biases and activations. And then we first get a by doing a matrix product with w. Then we will override a by saying a plus b. And then we will override it again by calling the activation function on a. And this state, if it is now activated, is what we will save in our container. So we will do layer states dot append a. Okay, this is the forward pass, but with the slight change that we saved the activated states. Then we can get the output of the network by just taking the value a at the very end of this loop. Then we compute first the loss by saying loss forward applied to y and y reference. And now we need to get our backward pass. And for this, we will use a similar strategy in that we have an intermediary variable, which we can actively override. And this intermediary variable is the current cotangent value. So basically it is y hat 4 bar and so on. So similar to the variable a we use in the forward pass, this is its cotangent counterpart. So in other words, whenever you hear cotangent, I mean this is taking the derivative of the loss with respect to that quantity. So let's go down and call this the current cotangent. And the value starts by calling loss backward on y and y reference. So this will be the y4 hat bar. And then we need to go backward. But before that, we will use a list in order to store the weight gradients and the bias gradients. And then we can loop reversely through our network by saying for W, F prime, a current and a previous. Okay, what do I mean by a current and a previous? So let's look at the backward definition. So here we go. When we are within one layer operation, so basically within one block, we need both the current value, so the y3 head saved, in order to do the backpropagation over the nonlinear activation function. But we also need the previous value to do the backpropagation into the current matrix. So when we are now looping, we essentially refer to each of the blocks here, and so we need both of them. Okay, let's go down again, and then we do that by going reversely over the weights, going reversed over the activations derivatives, going reversed over the layer states, excluding the beginning, and then reversed over the layer states, excluding the end. So now we have to think a bit. It's always hard to wrap your head around when it's reversed, but essentially this means now we take the layer states, but excluding the input to the network. From the 5 layer states we have, this will only give us the last 4. And if we then reverse that, we will start at the end. And so this what we call the current value. And then we do it vice versa here. So now we have only the first 4 out of the 5. And if we do it reversely, then we will start at the 4th and go to the first one, or to the beginning of this list. And this basically gives us the previous. And here this f prime, basically this shall be a function which defines the derivative of the activation function, but as an input it takes the output of the primal. So basically if we go to the sigmoid, so what we had here, this is basically a function which computes sigmoid prime, but without getting x, but with explicitly getting sigmoid of x, so the original output. Because that's the one we saved. We wanted to save only the activated state. We don't want to save the tilde state, which is the state after adding the bias. So this is just a nice trick and using this very nice property of the sigmoid function. Okay, let's get down here. Then we need our colon to start a loop. So then first we find the activated state cotangent by taking the current cotangent. So this is now basically doing a layer transition. So we go from the layer which is, chronologically after us, but in the reversed one before us. And now we have the activated state cotangent. So let's look at it here. So basically this is the y4 head bar. Now we want to go to the y4 tilde bar. So this is the plus bias state cotangent. And for this we will take the activated state cotangent and element-wise multiply. So this is what the asterisk does with f prime evaluated on a current. So if we then use the derivative of the sigmoid, this will be replaced by a current times 1 minus a current. So this is the plus bias state cotangent. Then we will first get the bias gradient. So let's look how it's done by doing the summation over the batch of the y4 tilde bar, which is the plus bias state cotangent. So let's go down. I think I got stopped here. So bias gradient is basically NumPy dot summation over the plus bias state cotangent of axis 0, because by convention the 0 of axis, so the rows, define the batches, and we only want to sum over the batches in order to retain the spatial or the hidden spatial dimension. Then we also get the state cotangent, and this is nothing else than the plus bias state cotangent due to the nice rule of pullback or backpropagating over addition. So this is y4 bar is y4 tilde bar. Next we go to the previous activated state cotangent, so the y3 head bar, by left multiplying it, matrix multiplying it with the transposed weight matrix. So we will need that one again. So this is the previous activated state cotangent, which is the state cotangent matrix multiplied. So again, the add with w dot transpose. And then we can define the weight gradient. So let's look at our overview of the backward pass again. And here the weight gradient was defined as the outer product of the cotangent state and the previous activated state. And I went over this, and there's actually a small mistake in there, which is caused by the confusion. I took that over from the Julia tutorial, and the correct way of defining the weight gradient or the weight cotangent here would be to have the y3 hat transpose and then the y4 bar on the right side. I think this should also be reasonable here, because we need to contract over the batch dimension. Since in the weight matrix we don't have any batch dimension anymore, so we only have the fan in and the fan out dimension. So in the rows it needs to have the fan in, and the fan in dimension is represented by the y3 hat. Originally the y3 hat is of shape batch by spatial, or fan in you might say, batch by fan in. And if we transpose it, we will get it fan in by batch. And then for the right, we will do the y4 bar. The y4 is of batch by fan out, and we don't transpose it. And if we then do a matrix multiplication, we contract over the batches. So I will quickly fix that, and then we will see each other again. Okay, here we go. Finally, now this is correct. So we now have the previous activated state transpose matrix multiplied with the current state cotangent. And we also have the same in the other blocks. And the only difference here is that in the weight matrix for the very first layer transition, we need the input again. And this is also the reason we kind of saved it, that we will reuse it here. Okay, with this down, let's finally define the weight gradient by saying this is a previous transpose, and maybe let me go up a little bit, matrix multiplied with the state cotangent. Okay, now we have both the bias gradient and the weight gradient. Let's append them to our lists. So we will do bias gradients dot append bias grad, and same for the weight gradients dot append weight grad. And then the last thing we have to do in order to ensure the consistency between the backward passes over the layers, we will set that the current cotangent is the previous activated state cotangent. So the current cotangent is the previous activated state cotangent. So we override this carry variable, and then the next layer further backwards down the line can also do its backpropagation. Okay, so this is the major parts of the backward pass. Now we're almost done with the function network forward and backward. So what does it return? So it should return the loss and also the gradient information. So technically it would return the weight gradients, but since we iterated over the layers reversely, these weight gradients are also now in reversed order, so we can put them back into chronological order by just reversing them. So a lot of reversing here. It can be hard to wrap your hand around it. Then we have reversed bias gradients. Okay, Shift Enter executes the cell, and now we have the function registered. So there was one thing left, that is that we need to define these activations derivatives. So for this, let us define the sigmoid prime first, which will be a lambda function, which takes as input x activated. Let's just call it like this, because again, it's a little bit hard also to wrap you around here. It's not the derivative function evaluated at the primal input, but it's the derivative function evaluated at the primal output. So here for the sigmoid, this is x activated element-wise multiplied with 1 minus x activated, and the identity prime will be a lambda function on x activated, which just returns 1. Then we can collect sigmoid prime and identity prime in a list that is similar to our activation functions list. So let's call this the activation functions derivatives. And this will now be a little bit of a hacky way in order to get that list. So basically what we will do is we say a list with one entry of sigmoid prime, which is repeated len of layers minus 2 times. So we have layers, length of layers minus 1 layer transitions. So 5 minus 1 is 4 layer transitions, out of which 3 layer transitions are with a true activation function. So therefore we do a minus 2 here. And then we will just append the identity prime at the end And now take a look at this. So basically this is now a collection of 4 lambda functions. The first 3 are the sigmoids and the last one is the identity prime. So let's now test this function that we have here, so the network forward and backward, on some dummy inputs. So network forward and backward, which takes the x samples, the inputs to the networks, the y samples, the reference supervised data that we have available. It takes the weight matrices. It takes the bias vectors. It takes the activation functions and the derivatives of those. Let's execute the function. And here, what does it return? So first we get the loss value and we can check this is exactly the same loss value as if we only take the forward pass. So having the additional backward pass does not change the numeric values or the numeric output of the forward pass. And then we basically get a reversed iterator. So this is nothing else than the list that we have with the gradient information. So let's hope that the gradient information is correct and we can do some training. So this is the final step. Now we have a routine in order to obtain a loss, which shows us how good the network is. It obtains a gradient, which gives us the direction into which we have to change the parameters in order to improve the loss. And we also have a starting point for optimization according to the random initialization. Okay, for the training loop, I also want to record the loss history. So basically, which loss value we had at which iteration. Then we do for epoch in range of n epochs. Technically, an epoch is the collection of mini batches, and here we only have one large mini batch, so all of our data at the same time. So you might also call it an iteration there. Then what we'll do, so we will first compute loss, weight gradients, bias gradients by calling our network forward and backward, similar inputs. So first the x samples, then the y samples, the weight matrices, or not the weight gradients, but the weight matrices, the bias vectors, the activation functions, and the activation functions derivatives. Then we will use our weights and bias gradients in order to update weight matrices and biases. And for this, let us also use some nice zipping. So let's say for W crad, B, and B crad in a zipped iterator, which takes the weight matrices, the weight gradients, the bias vectors, the bias gradients. We basically take matrix W and subtract from it the learning rate multiplied with the corresponding gradient. And for B, we will do the same, learning rate multiplied with corresponding gradient. So now we have updated this. Let's now print out some information to show us how good we are at the moment. So let's say if the epoch modulo 100 is equal to 0, so every 100 epochs, we will print out the loss by using a formatted string, by saying we are in epoch, and our current loss is loss. And then in each epoch, I want to append the loss to the loss history. So let's append it here, so then we can plot it later. Now let's execute that cell, and we see it is training. Our loss is going down. Beautiful, right? So we see we are epoch 30,000 now, and we have reduced our loss by a factor of 20. So it's not that much, but maybe it's already sufficient in order to get a decent network prediction. So first I want to plot the loss by saying plt.plot on the loss history, and then let's do logarithmic scale on the y-axis. Here we go. This is our optimization. So we started steeply first, and then there was nothing much more happening. Some oscillations actually took place here. So let's see how the found weights and biases perform now by doing plt.scatter again on the x samples and the y samples, and then we do a plt.scatter on the x samples and the network forward evaluated at the x samples, the optimized weight matrices, bias vectors, and of course the unchanged activation functions. So let's see. Here we go. Isn't that beautiful? I mean, we are evaluating it at the same points, data points at the scene, but that truly looks like a sine curve. right? It might still have some issues, but it is very close. And for the fact that this was such a quick training, I think this is an incredible result. Let me quickly summarize what we did here. For this, let me go to the intro doc string. And I believe that these three major, or you might call it 4 major steps that we do are essential. So first of all, we did our weight initialization because we need to somehow start with an initial guess in the parameter space. Then we have a forward pass, which just goes through the network and produces an output for us, which we can then see as some sort of a prediction of the network. We can do a backward pass, which requires us to do the forward pass and save deactivated layer states. So this is in accordance to reverse mode automatic differentiation, which also requires some sort of taping of the forward or primal evaluation. And this backward pass then produces cotangent information on all biases and all weight matrices. And if we started the reverse mode with 1.0, this is exactly the gradient of our loss. And that's super nice and allows us to do some learning. Here we restricted ourselves to a simple gradient descent optimizer. You could have used an Adam optimizer or something else. So what you get out of the backward pass is a general gradient estimate, and you're free to do with it whatever you like. And then we just repeated the process. With the new parameters, we produced new gradients and so on and so forth, and saw that our loss somehow converged. And there we got a beautiful prediction, beautiful state of the parameters that yields a network that somehow mimics a sine function. This channel is supported by Pasteur Labs and the Institute for Simulation Intelligence. Click the link in the video description to find out more how they merge machine learning and simulation in order to reimagine the scientific method. Also, a big thanks to all my Patreons. If you also want to support my vision of free education on advanced mathematical topics, you find the link to the Patreon page down in the video description. I hope you enjoyed this video. If you did, then please leave a like and consider subscribing. You might also be interested in the Julia version of this video, which I think Julia is a super nice tool for this. I believe it's even more concise than working with NumPy here. So you might also want to check that one out, or some other videos on automatic differentiation. I hope you enjoyed it. Here you will now see similar videos, and I hope to see you in one of the next videos.